Thank you, Chris. Yeah, it's exciting for me too. So what is SASyLF? The motivation for our work is that teaching programming language theory and proofs is hard. So some specific challenges are that it's very easy for students to get details wrong, and they can get very focused on those details and maybe learn some of the mechanics, but not learn the concepts. Another problem is that there's a slow feedback loop, right? If you turn in a homework assignment, you might wait a week for a corrected homework, or like a student of mine recently had to wait until mid-semester to get their first homework graded. This is not in my class, but that's a long time, and it's hard to learn. Okay, is that better? Okay, so in general, there can be a lot of high time and effort for the payoff you get. So tools could potentially help with this. They can check whether the details are correct. They could provide some immediate feedback, to students on whether they're doing the right thing or not, and maybe give them some hints as to what to do right. Not as good as a TA, but perhaps better than the student all alone with themselves. And maybe even eventually raise our productivity, right? Just like good compilers make programming more accessible. So what is there in this space? There's educational tools which are great for their domain, but aren't really about proofs. But we do have proof assistants and checkers. Right now, those are sort of mostly great for experts, right? I should add Agda to this list now, but they're very expressive. They have good automation, but they have a steep learning curve. And that's partly for the tool, just the syntax of the notation in the tool, but also for things like variable encoding techniques, right? How do you encode the notion of a variable in Coq? It's complicated. So one thing that inspired me when I started working on this, as Chris mentioned a decade ago, is that a 12 is a theorem prover that builds in variables. So it uses higher order type theory, and you don't have to encode variables because you can encode the idea that a piece of syntax depends on a variable right in the formalism itself. 12 also has explicit machine check proofs with small steps that students can follow. However, there's still a steep learning curve because it is based on higher order type theory. And so it can be challenging to use for undergraduate or intro graduate courses. So we designed SASyLF. The ELF is for Edinburgh's logical framework. SASy is for second order abstract syntax. We don't go all the way to higher order abstract syntax because of the limitations of our syntax goals. But let me talk about those. We want it to be easy to learn, familiar syntax, just like what we write on paper as much as possible. We want you to not have to have a lot of mathematical context, basically just understanding inference rules. We want to match programming language teaching approaches, so support for variable binding and alpha equivalence. We want explicit notation, because we want students to write proofs explicitly. This is maybe the opposite of what you want if you're familiar with programming in Coq, where you write scripts that are very high level and kind of the scripts write the proof for you. But we want the students to write the proof step by step in what an expert might consider maybe annoying detail. But for students, it's part of the learning process. Finally, rapid feedback. So an automated checker, of course, any proof assistant will provide this, and support for partial proofs. Finally, good error messages. So we want to give the error messages very locally in terms of what you're doing. What does this actually look like? So here is a little definition of natural numbers. And you can see kind of on the left what you might write in a paper. You can see on the right SASyLF. So we declare terminals Z and S. We have syntax with B and F. We define a judgment, and then we can write rules, with kind of ASCII syntax with the premises above and the conclusion below the rule. And so you see there's a pretty straightforward mapping. We can also write theorems. So SASyLF, like 12, supports for all exists theorems. For all n exists, n plus z equals n. Let me move the Zoom window out of the way so you can see the side. And okay, let's prove this theorem. So we have to show n plus c by induction on n. So there's a case for 0. 0 plus 0 equals 0. There's a rule for that. We can also use the induction hypothesis in the other case. And you can see things mirror pretty closely what is in the theorem. We may have to be a little bit careful about things like exactly how we name variables. We have to justify each step. We're giving a little more detail by saying not just the rule, but what's the thing that justifies the premise of this rule. But we actually think that's good for students to see that that logic very explicitly. I won't go through in quite as much detail the lambda calculus, but I will point out a couple of things. We can write E with X in brackets to say that X is a variable that's bound in E. And then, X stands for an expression. That means later we can substitute expressions for X's. It's built into SASyLF, and so variable X has type E. And then, we can write rules, and let's see, the most important thing is this third point here, right? We can do things like substituting an expression in, and that's again, something that SASyLF understands because binding is built in. And if you want to know why it's second order abstract syntax, well, we can quantify over judgments. Judgments have variables that represent expressions. Expressions can have variables that stand for expressions inside them. So there's two orders of quantification there. Okay, I'm going to skip like the types and the proof because I want to get to the usability. Let's see. Yeah, okay, so we've had some encouraging results. These are actually old results from the early days of SASyLF, but we hope to get some more results soon. We used it in a couple of courses. Students generally thought that it did increase their confidence in proof correctness, helped them find errors in proof. Some of them felt it helped them learn concepts. Others felt it was a barrier, but then the net feeling was positive there. Most people wanted to use SASyLF again and felt that it was fairly quickly to learn. We didn't get 5s on that, but we got above 3, which is the median on the Likert. And they felt that it helped them improve their ability to prove theorems even on paper. I did have a typo on this slide. Accomplished tasks more quickly should be 3.3. So that tells you actually people didn't necessarily feel like it was faster for them. But they did feel like it helped them learn. So that's encouraging. There were also some challenges. I think you can see, one of those is time. It is a tool that you have to satisfy like a proof checker, and so that can take time. And SASyLF is indeed picky. It forces you to teach proofs in a very rigorous way. So even though I think the notation is very close to what we teach, we have to do things like, how exactly does case analysis show that a tau that appears, in one place in a formula you're trying to reason about must be the same in this case as a tau prime elsewhere, right? So in a variable application, in a function application, the argument type of the function must be the same as the argument type of the type of the argument if the function application type checks, right? So reasoning backwards, you can find out that tau equals tau prime. We have to explain to students kind of exactly how SASyLF figures that out. John Boyland, since we created the tool, John Boyland added a very nice notation that adds where clauses so students can kind of state when they learn that two variables are equal and kind of state the equation. So that's been helpful. But there is kind of this pickiness that goes with proof assistance. And some steps end up feeling pedantic. For example, if you do a case analysis on typing, if you want to show that parentheses like a unit value can't have type Boolean, you actually have to do a case analysis on that and show, if I know this is type Boolean and I'm doing a case on the syntax and I consider case unit, well, I can't have type Boolean, so this is impossible, right? So we sort of hoped you wouldn't need a tutorial at all for SASyLF, but you do need one. There's just some pragmatic tool issues. We use GLR parser, which is kind of a cool trick. It can parse ambiguous grammars. So the user can just write any grammar they want for their language, and most of the time they are ambiguous. But if you put in parentheses, the parentheses disambiguate. The parentheses are kind of built in as a way of grouping things that would otherwise be parsed ambiguously. But students need to be taught how to do that. And there's a set of issues that are kind of similar to that. I think the tutorial is a lot shorter than it would be, for kind of a professional tool, Coq, AGDA, 12. But we do need that, and actually we need a better one than we used in the class that I'm teaching this year. So I need to improve that. We got some experiences from students. There's a couple of interesting quotes here. The danger of kind of autopilot tool use. So one student told us, on trickier proofs, I had to go to paper to clearly state what I was trying to prove. When using the checker, instead of thinking about how to make a beautiful statement that reveals something true, I was just concerned with jamming the nuts and bolts together until the checker was happy. Okay, so maybe an interface can make SASyLF more beautiful, but maybe we actually, when teaching, even if it's a useful teaching tool, maybe we should go back and forth between paper and tool proofs, and that's been something that's other educational researchers have found when trying to teach formalisms. I think Michael Greenberg mentioned that in one of his papers. Some students did make comments about how the tool helped them as well. So one student said, I did the whole assignment on paper first, and I found it very easy. But once I started using the tool, I started understanding the concepts better. People report that the tool, made them think about, hey, do I need to prove 1 + 1 = 2, or I + 1 = 2 when I = 1? So thinking about the subtleties of exactly what they're proving, which is maybe a stepping stone towards thinking the right way about proofs. And then thinking at a higher level, right? Because I have more confidence in the logical flow of my proof, I could spend more time on the bigger picture. So some people actually felt the tool helped them think big. So I have some discussion things. I guess our discussion session is at the end. So we could use a couple of minutes of my time for a preliminary discussion here and then have a bigger one later. But I think actually there was a couple of interesting questions raised by reviewers. How much could be done of this could be done in professional tools. There is something called OT, where you can write the syntax and rules much like SASyLF, and then it translates them to Coq for you. But then you have to do the proofs in Coq, and so you still have to learn all of the Coq tool. So I think that doesn't actually help with our approach. And error message, the fact that we give error messages that are very local and are in terms of SASyLF's abstractions, including binding, I think is an advantage that would be very hard to replicate unless you really did something that like SASyLF, kind of built-in semantics at the level of which students teach. Yeah. Anyway, I don't know. Do people have comments? I think I have like a minute and a half left. If people have comments or questions.